Well, to come back to the properties of ideal solutions. So, therefore, the first property we had already discussed in the last class, where I told you that the ideal solutions are formed with no change in volume, right. Let us see what are the other properties. They will all come from the properties of the fugacities that we have dealt with. I had already mentioned to you how fugacity changes with pressure. It changes with temperature, right. So, therefore, in that particular case, suppose we write it down, what do we get? Del ln Fi by del T at constant P, this is nothing but equals to Hi bar minus Hi0 by RT square. And what about this term also? If you refer to full screen, if you refer to this is Hi0 minus Hi by RT square, right. So, therefore, from this particular equation, what do we get? We get this. Now, from here what do we get? We find out that the partial molar enthalpy of component I is equals to the molar enthalpy of component I. In other words, which implies that the components mix with no absorption or evolution of heat. They mix with no absorption or evolution of heat, right. And that is quite expected. Why? Because I have already mentioned that this is applicable when the interactions between unlike and like molecules are the same, which automatically implies that when they are mixing, there is no extra energy added or no extra energy evolved during this particular process. So, therefore, if this is correct, then what about the enthalpy, molar enthalpy of mixing? What is the molar enthalpy of mixing? The molar enthalpy of the components after mixing minus the molar enthalpy of the components before mixing. After mixing, what is the molar enthalpy of the components? This is Xi Hi bar sigma. And what were the molar enthalpy of the components, or what was the enthalpy of the total enthalpy of the components when they were kept separate to each other? That was Xi Hi. The total proportion, or rather for 1 mole of the mixture, when the components were kept separately for each particular component, this was the molar enthalpy taken together, and after they mixed, the molar enthalpy changed to partial molar enthalpy. So, therefore, the enthalpy of the molar enthalpy change of mixing is given by this particular equation, which can otherwise be written down as Xi Hi bar minus Hi. We know that these are equal. So, therefore, the molar enthalpy of mixing is 0. In the same way, just like we can also write down the molar volume change of mixing is also equal to 0. Now, what do we know? We know H equals to U plus PV, or in other words, we know U equals to H minus PV, or delta U equals to delta H minus P delta V. The whole thing is being carried out at constant pressure. So, therefore, in this particular case, suppose I take that before mixing or rather if I take the molar internal energy change on mixing, this should be equal to delta H mixing minus P delta V mixing. Already we have proved this equals to 0, this equals to 0, which automatically implies delta Um equals to 0. You can just notice that I have mentioned all these equations. So, therefore, we find from here, what do we find? We find that when ideal solutions are formed, they are formed with no change in volume, they are formed with no evolution or absorption of heat, and no change in the internal energy of the solution, quite naturally. What about the Gibbs free energy change of mixing? Does that also disappear, or there is some Gibbs free energy change of mixing when the two components are mixing, even when they form an ideal solution? Let us see what is delta Gm equals to. This delta Gm, this should be equal to, suppose this is again, suppose I take up the capital Gm, right. This will be equal to your G of pure liquids before mixing minus G of liquids in solution, right. Now, what is the G of pure liquids? Let us see. For the time being, let us consider a binary mixture, 2 component solution. Okay. So, therefore, before mixing what was this? This was Na mu A of pure liquid. So, therefore, I do not put anything, just in case you get, but for after this I am not going to write pure liquid, plus Nb mu B. Fine. What is G mixture after this A and B have been mixed? This will be Na mu A. Again I would like to remind you that mu also has the same property of fugacity. So, they are also shown by a cap here. So, therefore, in this particular case, since I have written down G pure liquids, I have written down G mixture. So, therefore, from here I should be in a position to find out delta G mixture. Just subtracting what is delta G mixture in this particular case, you tell me. This is nothing but equal to Na mu A bar minus mu A plus Nb mu B bar minus mu B. Fine. Now, you tell me how are this mu A and mu A bar related to one another. Is mu A bar not equal to mu A plus RT ln x A? Isn't it? Does this relationship hold or not? Again, I would like to remind you from where did this relationship come? It came from the Gibbs-Duhem equation. What was Gibbs-Duhem equation? What did I find out? If you remember, xi d mu I equals to 0. This was Gibbs-Duhem equation, right. So, therefore, in this particular case, suppose I would like to integrate it from your xi, or in other words, this is x1 d mu 1 plus x2 d mu 2 equals to 0. So, therefore, this comprises of component 1, this comprises of component 2. Now, suppose I integrate it from x1 equals to say 1 to that is the pure component, to x1 equals to x1. Suppose I perform that particular integration, then we find that this gives us your mu A minus mu A bar, which is nothing but equals to RT ln x A. Same way we can write down mu B is nothing but equal to mu B plus RT ln x B, right. So, therefore, from here what do we know? We know that G mix minus G pure liquids, which is nothing but equal to delta G m. This is nothing but equal to Na mu RT ln x A plus N B RT ln x B. So, therefore, what is the molar Gibbs free energy change of mixing? This is nothing but x A RT ln x A plus x B RT ln x B. So, therefore, for I components for n number of components, we can simply write delta G m, it is sigma x I ln x I R T I equals to 1 to n. If you recollect, this is similar to the molar Gibbs free energy change of mixing for ideal gases as well, right. So, we find that delta G m is not equal to 0 if the components form an ideal solution. So, therefore, if delta G m is this, what about your delta S m, the entropy change of mixing? We know delta S m should be equal to delta G m minus, it is by T minus delta H by T, isn't it? We know G equals to H minus T s. So, therefore, T s is nothing but equals to H minus G, or in other words S equals to this, sorry. So, this is going to be plus, this is going to be minus, fine. We know this term your delta H m 0 is 0. So, therefore, what is delta S m? It is nothing but minus of delta G m by T, which gives you, as in this particular case, this gives you minus R sigma x I ln x I, right. And in this case, I would like to tell you that since x I is less than 1, delta G m will always be negative if the solution has to be formed. And again, I would like to remind that we are dealing with solutions which are miscible in all proportions. and again we know that delta Sm is greater than 0 for a solution to be formed. These are with in line with what we have discussed till now. So, therefore, I have jotted down all the properties that I have mentioned, and these are the properties of ideal solutions. We find that the ideal solutions, they are accompanied by no volume change of mixing, no absorption or evolution of heat, no change in internal energy, but with an increase in the randomness of the solution. And just because there is an increase in randomness of the solution, that is why this, the two components, they mix spontaneously to form an ideal solution, and it is this particular entropic effect which gives you a negative Gibbs free energy change of mixing, due to which the solution mixes. It is not due to the enthalpic effect, it is due to the entropic effect. Now, therefore, so suppose I give you a solution and I tell you to find out whether it is ideal or not. We can definitely take we can measure the two volumes of the components that we are taking, we mix them up, and then we measure the volume of the solution formed. We find that there is no change in the volume of the solution. We can assume that the solution is ideal. But in this case, there is something that you need to remember. There are certain instances where we find that under specific composition, the solution might behave ideally. That in no way implies that the solution exhibits ideal behavior over the entire range of composition. For example, suppose say we find that we take up a solution of say your benzene and ethyl alcohol. For this particular solution, suppose we take this particular solution and we try to plot the molar volume as a function of say benzene, right, where A is benzene. We find that from 0 to 1, if we take, we more or less find that the graph, it varies in this particular form. We find that initially there is an increase in the volume of the volume of the solution on mixing, and then there is a decrease of the volume of solution on mixing. At one particular xa, we find that the volume of mixing is 0. Or in other words, at one particular xa, we find that there is no volume change on mixing. The volume initially and after mixing are the same. So, suppose we take up these two components and we try to see the volume change on mixing at this particular composition, then automatically we think that the solution is ideal, but it is not ideal. It deviates from Raoult's from the Louis fugacity rule, but if you are testing it under one composition, you might get you might get it means you might get a wrong result. The same thing can be applicable for enthalpy change as well. And so, therefore, it is very important that when you are testing for ideality of a solution, you perform the experiments over a large range of compositions, so that if it is valid over a large range of compositions, then it is ideal. Or in other words, the safest test for finding out is if it is at low to moderate pressure, then I have already mentioned that for low to moderate pressure, what is Fi? Fi is the fugacity of pure component I in the at the temperature and pressure of the mixture. Suppose I am dealing with a liquid solution, then for low to moderate pressure, the Poynting correction factor is 0, and the non-idealities due to the non-idealities of the gas phase, that particular correction factor is also 0. So, therefore, Fi it reduces to Pi saturated, and under that condition, what is this equal to? This is Xi into P, or in other words, sorry, this is the partial pressure, isn't it? So, for low to moderate pressure, this reduces to Pi equals to Xi Pi saturated, which as you all know, this is nothing but the Raoult's law, right. So, the safest thing is if you plot the partial pressure as a function of molar volume over the entire range of pressure, and to see that and to see that you get a linear curve in this particular fashion, then you know that the solution obeys ideal solution model. So, therefore, an ideal or a very safe test to test the ideality of solutions is not to test the volume change of mixing or the enthalpy change of mixing at very few mole fractions. We can do it over a large range of mole fractions, or else the safest thing is just find out the partial pressure and plot the partial pressure and to find the linear plot. In other words, we will find that in fact, suppose there are two components, maybe component 1 and component 2, and then suppose we plot the partial pressure of both the components here. So, for x 1 what do we have? We find that when x 1 equals to 1, then the partial pressure is equal to the pressure of the component. This is equals to P 1 saturated, and when x 1 equals to 0, this is going to be P 2 saturated, right. Now, usually 1 is our more volatile component. So, therefore, at constant temperature, if I try to find out the x 1 at, if I keep on varying x 1 and I try to plot the partial or rather the partial pressure, then I get a curve of something of this sort. For component 2, the curve will be something of this sort, and therefore, the total pressure in this particular case, it varies from P 2 saturated to P 1 saturated in a linear fashion. So, the simplest way to do is what? You find out, you mix two components in different proportions, find out the total pressure over the mixture, plot all the points, and if you find that all the points more or less fall in a straight line, which varies from P 2 saturated at one end to P 1 saturated at other end, then we know that the solution is ideal. This is a shear test of ideal solution. Well, so once we have understood an ideal solution and we have understood under what conditions ideal solutions are applicable, what is the next thing that we should do? We should find out, ultimately we are dealing with phase equilibrium thermodynamics. So, what we should do? We should find out the phase equilibrium relationships for ideal solutions in the vapor and the liquid phase. What do I mean? I mean, suppose I have got the simplest solution, a two component solution, component A and component B say, and they are there is a liquid solution in equilibrium with its vapor phase. So, therefore, component 1 and 2 they are present both in the liquid phase as well as in the vapor phase. Now, for the liquid phase, suppose I say that in the liquid phase the solution is ideal, then in that case I know Fi liquid, this is Xi Fi. In the, I say that the vapor phase also exhibits the properties of an ideal solution or ideal mixture. So, in the vapor phase what can I write? Yi Fi, this is L, remember this is V. Again I remind, the phases are given as subscripts, the component numbers as superscripts, component number as subscripts, and these are the partial molar properties, these are the pure component properties, right. So, therefore, in the liquid phase this is the equation, in the vapor phase this is the equation. If I assume that the vapor and the liquid phases are in equilibrium, if vapor and liquid phases are in equilibrium, when is it possible? We know we have already framed the conditions of equilibrium for the two phases in terms of fugacity we have already done. So, fugacity of each component must be same in all the phases, or in other words this should apply. For if we write it down in terms of pure components, this particular function should apply. At low to moderate pressures, I have already mentioned, at low to moderate pressure what happens? FIV equals to the total pressure over the mixture. FIL is equal to the saturated vapor pressure of the pure component at the temperature of the mixture. So, it is Pi saturated at the temperature of the mixture. So, on substituting these, what do I get? I get at low to moderate pressure the equation for phase equilibrium reduces to this. This is the most important equation that we use for finding out the phase equilibrium problems, and this along with the additional constraints that sigma xi should be equal to 1 and sigma yi equals to 1, this whole set gives us the different phase equilibrium problems that we come across for two component systems of a two phase mixture, right. So, in this particular case therefore, if it is a two component, then what is f, what is the minimum number of what is the degree of freedom in this particular case? We know f equals to c minus p plus 2, this is 2, this is 2. So, therefore, f is also equal to 2, right. So, therefore, what are the total number of variables? The temperature of the solution, the total pressure, the mole fractions in the liquid phase, mole fractions in the vapor phase. And we know that x 1 and x 2, they are related by x 2 equals to 1 minus x 1, these two are related by y 2 equals to 1 minus y 2. These correspond to this particular condition, right. So, therefore, these are related. So, therefore, basically we have 4 variables, fine. Out of these we know for a two component system, just 2 variables can be varied at will, the other 2 automatically gets fixed up. So, what are the things that we can vary? The different things which we can vary are, we can vary the either the temperature, either T and X, we can we have T and X, we can vary P and Y, we have T and Y, we can vary P and X, and so on and so forth. So, therefore, these are the 4 sets of things that we can vary, and these are the 4 ways that we can vary the 2 variables, and accordingly if we vary the 2, the other 2 has to be calculated accordingly. So, before we do a number of problems, the next thing which I would like to discuss are some phase diagrams for binary mixtures. Well, before that, it is important for you to note that for a binary mixture f was equal to 2 for n components. N components, what it becomes? F equals to c minus p plus 2. This is n, this is 2, therefore, f equals to n. So, therefore, for n number of components, we find that the degrees of freedom is n, and out of here we have T p x 1 to x n, again bounded by the constraint of sigma x I equals to 1. So, therefore, x 1 to x n minus 1 if I know, then automatically I know x n, and y 1 to y n minus 1, which will automatically give me y n. So, this is my range of variation. Out of this I can vary just n number of components. It can be the total n minus 1 compositions temperature, n minus 1 composition pressure, or n minus 1 compositions the vapor phase temperature, n minus 1 composition vapor phase and pressure. So, any of these permutation combinations are done, usually they are done either at constant temperature or at constant pressure, and accordingly we generate either isothermal xy data, we will be doing a few problems, or maybe isobaric xy data, right. And so, therefore, in the next class what we are going to do is, in the next class we are going to discuss the different phase diagrams primarily at constant temperature and constant pressure. At constant pressure temperature we generate the pxy plot, and at constant pressure we generate the txy plots. We will be discussing these in the next class.